Okay, hello everyone, and let's start another session of verification. So let me share the screen. Hopefully you can all hear me. If you can't, please say in the chat. Okay, no one said anything, so you can all hear me. Great. So today we're going to actually start a new module, and we're going to talk about a logical approach to verification. We're going to talk about linear temporal logic. But before we do that, let's just take a look at what we've seen until this point. So we saw two-player infinite duration games on graphs. And the thing that I really want to focus on right now is that in these games, we had sets of infinite words. Basically, every play of the game was an infinite path on the graph game, which you can consider as an infinite word as well. And then the objective of a player, for example, the objective of player one was just a set of infinite words, right? And then also another set of infinite words that we were really interested in was that if we fix a strategy for player one, and just take all the possible outcomes of the game, starting from the starting vertex, using this strategy for player one and any other strategy for the other player. So this gives you a bunch of different outcomes. And this set is also a set of infinite words. So when we wanted to see whether player one has a winning strategy, what we were looking for was actually a strategy sigma 1, such that this set of outcomes, the set of outcomes that's obtained by playing sigma 1, no matter what player 2 plays, is a subset of the objective of player 1, right? So when we were talking about the games, basically what we were really interested in was that we have two different sets of infinite words, and we want to see if one of them is a subset of the other. Okay. Now, after that, we went on and talked about automata and infinite words. We defined different types of automata, Bookie, parity, and Rabin. And we showed that deterministic Bookie automata are not as expressive as the rest of them, but then in the non-deterministic case, all of them have the same expressivity. But then if you look at what we were doing with automata, if we have an automaton A, then the language of A is what? It's also a set of infinite words. Right? And the intuition that I gave you for how we use automata to verify programs was that suppose that I have one automaton A that accepts all runs of a program, and then I have another automaton B that accepts all runs that satisfy some specifications that I have. So B accepts all the runs that do not have any errors in my point of view. Okay. If I have this kind of basically program automaton and specification automaton, then the correctness of the program basically boils down to whether the language of the program automaton is a subset of the language of the specification automaton. So again, here we have two sets of infinite words, and we want to see whether one of them is a subset of the other one, just like here. And actually, this was the reason why we studied complementation and emptiness checking, because using complementation and emptiness checking, we can also check whether the language of one of the automata is included in the language of the other. So in this session, what we're going to do is that we're going to basically look into yet another way of defining and specifying sets of infinite words. And this is the logical approach. And the logic that we're going to look at is called LTL, and LTL stands for linear time temporal logic. So let me just say a few words about the name. Well, you know what a logic is. It's temporal in the sense that it models time. So time has really a central place in this logic. And then it's linear time because the way that this logic looks at time is basically linear. You have a time 0, time 1, time 2, so on, and the time goes on linearly. So you have one state of your program or your system at every time. Okay, so let's start. First of all, because we want to be able to do logics, we definitely need to have some notion of propositions and atomic propositions. So let's say that I have a set P, which is finite, and this is the set of my atomic propositions. So P is a bunch of facts that can hold or not hold at any given time. Okay, and that's the only thing that we know about them. They are atomic in the sense that we don't know anything else about them. We just know that P is a finite set, and each proposition in P might or might not hold at any given state. Okay. So the language that I'm going to use is based on the alphabet sigma. And sigma is basically all subsets of my atomic propositions. So the way you can think of this is that if I have a bunch of propositions at a given moment right now, for example, some of them are true and some of them are false, right? So my state right now would be a subset of the propositions that I have. And then I just define one other word, and that's trace. A trace is simply an infinite word over this sigma. So a trace, which I show with tau, is basically any infinite word in sigma omega. Okay. So here's a very basic example. Consider a traffic light. Let's say that it has 3 different lamps for red, green, and yellow. So our basic atomic propositions can just be red, green, or yellow, and each of these can be on or off, right? So our traffic light has 8 states overall, because 2 to the power of 3 is 8. And actually, in a correct implementation of this traffic light, only 3 of these states can occur, right? So you shouldn't really have 2 colors at the same time, unless your traffic lights are weird. So if you just look at a traffic light and just write down all of its transitions and how the lights go on and off, this is actually an acceptable run because, well, it was red, then it became green, yellow, red, green, yellow, and so on. But this is unacceptable. Why? Because, well, at some point here, you have all 3 lights on. So this is red, green, and yellow, all of them are on. And this is also unacceptable because at some point you have all lights off. Okay. So the thing that I really want you to note here is that RGY, all of it is just one letter, right? Because my letters are now sets of propositions. So this basically means that RG and Y were on at the same time. But this one means that at time 0, R was on, then at time 1, G was on, then at time 2, Y was on. So this is really important. Okay. So if we want to make sure that only these 3 states, only red, green, and yellow can occur, then we can basically write an automaton that only accepts the set of strings, the set of infinite words that have these states, right? And it's quite easy to write such an automaton. You just need a few states. You start somewhere. As long as you haven't seen any of the prohibited states, you stay in the initial state. And as soon as you see something that is prohibited, you just go to some sink that rejects the word. So you can do this with Bookie, Parity, or Rabbit. But what if I want to actually treat this as a logical formula? How can I write it as a logical formula? So here's the thing. What I want is that I want to, first of all, think of each letter as happening in a different point of time. So at point 0, this is the state of my system. At point 1, this is the state. At point 2, this is the state. Okay. Now, what I want to say is that I want a really nice property to hold at every point in time. So at every point in time, I want to be sure that at least one of my lamps are on, at least one of the colors are on. And I also want to make sure that no more than one is on. So it's not that both red and green are on or both red and yellow are on. So as you see, this is just a basic formula in propositional logic. and we have these atomic propositions. We can do all sorts of logical things with them. But what's really interesting is that we are saying at every point in time, I want these things. So this is the temporal aspect. Okay, so let's see some more examples of these temporal properties that we like to have for, again, let's say a traffic light. So what does this first one say? It says at every point in time, either the red light is off. If either the red light is off, oh no, not either. Okay, sorry, let's do this again. This says that at every point in time, if I know that the red light is off right now, and also I know that in the next step, in the next point in time, the red light would be on, then from this, I should be able to deduce that right now the color is yellow, yellow light is on, right? This makes sense. It basically means that whenever you're transitioning into red, you have to transition from yellow into red. You can't transition from green to red. Okay, so note that we have now two different temporal operators here. One is that we're saying at every point in time, we want something to happen. And then there is also this one in the next step. I'm referencing what happens in the next time point, basically. Okay. Or here's another one. So let's say that you're a car and you're approaching this traffic light and you want to be sure that you can actually pass it. So in order for you to be able to pass it, this is the property that should hold. This is basically usually called liveness. At every point in time, there should be some other point in the future such that the light is green at that point. Right? So no matter when I arrive, I'm sure that if I wait for finitely many units of time, there is some point in the future where it would become green and I can go. Okay. So this is the third operator that we're seeing, that there is a point of time in the future where something happens. Okay. And of course, we can have many combinations of this. For example, this one says that at every point in time, if right now the light is green, and in the next step the light is not green, then in the next step the light should be yellow. So it can't go directly from green to red. It has to go through yellow. This one basically just says that yellow is used at least once. So there is a point in time where you have yellow. What does this one say? What does this one say? It says that right now, see, there is no quantifier at the beginning saying that at every point in time. So when there is no quantifier, we are talking about right now, and right now means time zero. So this says that at time zero, the light is yellow. Sorry, at time zero, if the light is yellow, then the light remains yellow until at some point it becomes red. Okay, so we will see a more formal definition of this until. Okay, so let's just give some formal names to these operators that we had here, and let's define a syntax. And while I'm defining the syntax, I'm going to also informally tell you what the semantics are, but then of course we're going to go into it and define the semantics formally as well. Okay, so again, let's say that we have our set P of propositional atoms or atomic propositions, and our alphabet is the set of subsets of our atomic propositions. And we are looking at traces, which are basically infinite paths over this alphabet. Okay, so here's the syntax of how you can create an LTL formula phi. So an LTL formula phi can just be true, or it can be one of the propositions in P, or we can have or phi1 or phi2. We can have negation. And then there are two more. And these are the temporal operators that I will define right now. Okay, but before defining that, note that this already includes propositional logic, right? Because anything else that you did in propositional logic, I can just define as syntactic sugar. For example, I can define false as the negation of true. I can define and using or and negation. So phi1 and phi2 is basically the negation of not phi1 or not phi2, right? And I can also define entailment and so on. Okay. So let's see what we mean actually by these things. So true is obvious, right? So true is something that is always true. It's just. Now, when I write P is one of my atomic propositions, right? But I have a run of my system, and the run of my system is an infinite word. It's an infinite trace. So when does an atomic proposition hold on an infinite trace? Well, basically it holds if it holds right now at time 0. So P holds in this whole trace if it holds here. Okay. So for example, if my formula is just R, what it tells me is that the light is red right now. At time 0, the light is red, right? And if it's R and G, it says that the light is both red and green. So both the red and the green are on right now at time 0. Okay. So this is how we handle atomic propositions. And then I'm sure you know how to handle or and negation and things like that. Those are the easy ones. The ones that are actually interesting are the temporal operators. So we have this operator, which I read as next phi. And next phi means that I am claiming that phi holds in the next step of time. And sometimes instead of a circle, they just use an X. So circle phi or X phi are the same. And they're basically saying that this formula phi should hold starting from point 1. So we basically ignore point 0 of time. We ignore right now. We go 1 second into the future and say, okay, from now on, phi should hold. Okay. So if I have, for example, next R, this means that the light will be red in the next point of time, in the next second, for example. And the last operator that I have here is basically until, and this is the until that I was using here. So when I say phi1 until phi2, what I mean is that here, basically the formula phi1 should hold until there is some point in time where the formula phi2 holds. Okay, so this means that there is some index, some point in time from where phi2 holds, and at every index before that, phi1 holds. Right? So if I write something like this, G and G until R, this means that the light is green right now at time 0, and the light remains green until at some point it becomes red. Okay. And note that I don't care about the other details. So phi1 might hold here as well. I don't care. The only thing that I care about is that there is some point in time where phi2 holds, and at every point before that, phi1 holds. Okay. So this is the definition of until. Now, the thing that is actually a little bit confusing about all this stuff is that phi1 itself is a formula in LTL, right? And a formula in LTL can actually talk about the future. So for example, phi1 can be next R. Then in that case, phi1 can hold here, and whether phi1 holds here actually depends on the rest of the word. Right? Or phi1 itself can have until in it. So it can actually, when I say phi1 holds here, what I really mean is that phi1 holds for the suffix that starts from this point. Okay? So we're going to see that very soon. Let's see the formal definitions very soon. But before we do that, let's just define some more syntactic sugar. And these are actually the temporal operators that we use more often, but it's just more elegant to use them as syntactic sugar. Okay, so we have this diamond thing, and we read it as eventually. So this says eventually phi. And what it means is that there is some point in the future where phi holds. Okay, so if this is my infinite word, my trace, there is some point in the future after finitely many steps where phi holds. And again, when I say phi holds, I mean phi holds on this suffix, right? Suffix. And people also write this as f phi. And usually when they do this, they mean that in the future phi holds. So that's why they use f. And we can define this as syntactic sugar, right? And the way that we can define this as syntactic sugar is that eventually phi is the same as true until phi. So what does eventually phi say? It says that there is some point where phi holds. Well, and true holds all the time, right? So if I say true until phi, this is the same thing. There is some point that phi holds. And of course, true holds all the way until that point. Okay? So if I have eventually R, this means that the red light will eventually turn on, or the light will eventually turn red. Okay? And then we have the dual of this basically, and we call this globally or always. So always phi means that at every point of time, the formula phi holds. And this is also sometimes written as G phi and for globally phi. And again, this is so the pictorial representation. So phi holds at the beginning, it holds at step 1 and step 2, it holds basically all the time. So for example, when I say this, when I say that always I have the property that oh, okay, I forgot something here. So when I say I always have this property, it means that the light never turns off. So there is no point in time where all the 3 colors are off, right? And now again, I can define this as syntactic sugar. How do I define this as syntactic sugar? Well, I just use the dual that I had here. So always phi is the same as not eventually not phi, right? Why? Well, always phi means that phi holds all the time, right? So there is no point in time where we have not phi. And that's the same as saying not eventually not phi. Okay, so this is how we define the basic temporal operators. And this was the syntax of LTL. Are there any questions until this point? Okay, so let's see some examples and let me ask you what each one of these do. So what does this one say? Please write in the chat or talk. So diamond Y, what does it say about our traffic light? Yes, it says that eventually the yellow light turns on, but it doesn't say anything about the other lights. So it doesn't say that eventually you only have yellow. It says that eventually the yellow light turns on. Maybe at the same time other lights are on as well. Okay, great. So what does the second one say? So this is basically saying if Y, then Y until R. What does it mean? if the light is yellow now, it will be yellow or red. No. So this is until. Basically, what it says is that if the light is yellow now, then there is some point in the future where the light becomes red. And at every time before that point, the light is yellow. Or actually, to be even more specific, if the yellow light is on right now, then there is a point in the future where the red light would be on. And at every point of time before now and then, the yellow light would remain on. Okay, so we're not saying anything about the other lights. For example, green can just flash. But the thing that is really important is that this Y, this is only checked at the beginning. So it's only checked at time 0. This doesn't say anything about the entirety of the future. It doesn't say that at every point in time, if it's yellow, then it eventually becomes red. What it says is that at point 0, if the light is yellow, then we have this. So, for example, any trace that starts with the yellow light off would satisfy this, right? Because the precondition does not hold. Okay. What does this third formula say? And really note that I need to put these parentheses in. The parentheses are important. Any ideas? If the light is not red and it turns red next moment, then the light is yellow now, always holds. Yes, okay, that's correct. So basically at every point in time, if you know that at that point, the red is off, but then in the next point, red becomes on, then you know that at that point, yellow is on, right? So whenever you transition to red, you transition through yellow. Okay, but what does this one mean? Now I'm just removing one of the parentheses. Just to show you how important it is to put parentheses. Yes, actually, it's really hard to put it into words. The thing in chat is kind of correct. Yes, that's correct. Yes. So basically what it says is that if, and this is the condition of the if at every step of the time, the red light is off, but then in the next step, the red light is on. If this whole thing holds, then we know that the yellow light should be on at step 0. So this Y here is only referring to Y at step 0, and this is why you need to put parentheses. And actually, this is impossible, right? So it's impossible that at every state, you have not R, but then in the next step, you have R. So this is basically false, right? The precondition is false. So this says nothing overall. Just removing a parenthesis made it so that we say nothing. Okay, what happens if we remove this next parenthesis? What does this one say? It basically says that if at every point in time, the red light is off, and only at point 1, so the next time red is on, then y should be on at time 0. And again, this is of course false. The precondition is false, because if at every time red is off, then you cannot have red be on at time 1. So again, this is nonsense. Okay. What does this one say? Yes. So it says that at every point in time, if we know that green is on and in the next step green is going to go off, then we know that in the next step yellow is going to go on. Right? So it basically says that whenever we transition out of green, we transition to yellow. Okay, what does this one say? So eventually yellow or not next red. What does this mean? Sorry, always yellow or not next red. It means that at every point of time, either the light is yellow, or we are sure that in the next point, the light would not be red. So this is again saying that if the light is red at some point in time, then right before that, the light should have been yellow. And this applies to the whole, to every time, right? Okay. Now let's look at these two. These are nice. What does this one say? It says always eventually G. What does this mean? Okay, so one person says it just means eventually G. No, because, well, here's the thing. If you have, for example, this E, Y, G, and then E, sorry, we didn't have B, we had red, sorry. So red, green, yellow, and let's say that we remain in yellow. Then this is eventually G. This satisfies eventually G, but it doesn't satisfy all this eventually G. So Yao Zhou is right. G turns on infinitely many times. But no, this is not that the same as sometimes we have the light turning to green. So here's the thing. Sometimes the light turns to green would accept this string, which starts with red, green, and then stays in yellow, right? But what we're saying is that at every point in time, we have eventually green. So if I cut this at every point and take its suffix, for example, if I cut it here, and only take this suffix, then it should have green in it, right? So always eventually green means that at every point in time, always, there is a point that comes later in time, eventually, that is green. So this is the same as saying that we see green infinitely many times. What if we swap the two operators? What if I say eventually always green?
same as eventually?
No, because always green is not the same as green, right? So what does always green mean? Always green means that from this point onwards in time, green is always on, right? Yes, so the answer in chat is actually correct. So after, well, we will only have, no, sorry. So we can't say that after some point we will only have green on. What we can say is that after some point, green will always be on. And it doesn't say anything about the other lights. So here's the thing. What does eventually followed by anything mean? So if I had, let's say, eventually, so copy from here because it's really hard to type these things. So if I have eventually y, what does this mean? This means that there is some point in time such that if I ignore everything that happened before this time and only look at the future from this point onwards, it satisfies the formula y, right? So when I say eventually always green, this means that there is some point in time. So I'm ignoring a finite prefix of my trace and saying that there is some point in time where from this point onwards, green is always on. Okay. So in other words, always eventually green is very different with eventually always green. Okay. And actually, there are many use cases of this that I can easily think about. So suppose that you have, for example, several processes that are using the same resource. For example, you have a printer and there are several different processes who want to use it. Then the way that we usually handle this is that we have a lock L, and the lock will have an owner at every point in time, right? And when we want to basically handle mutual exclusion, handle the requirement that no two processes should have the lock at the same time, we can write it like this. We can write that always it is the case that either process 1 does not have the lock or process 2 does not have the lock, right? Or if you consider a web server, and let's say that this server gets some requests from the client and it should acknowledge them, or it should give some sort of response, then the property that we want to hold is that we want every request to eventually get a response, right? So we want to have this property that always, if there is a request from the client, then sometime in the future, there would be an acknowledgement from the server. Okay, so now that we saw all these examples of LTL formulas, and okay, before going on, I have to say this, it takes some time to get used to these things. So you have to work with them for a long time. And it's a bit unsettling that, for example, always eventually and eventually always are not the same thing. But I guess you had the same problem the first time you were introduced to first order logic and you were working with quantifiers. So these are also very similar. They're just like quantifiers, but they're quantifying on time. You can think about it like this. Okay. So formal semantics, of course, because this is a semantics course. So now we want to formalize what these formulas in LTL actually mean. Okay, so let's say that I have a formula phi, which is an LTL formula. So I have to define the meaning of phi or the semantics of phi. And this is very similar to what we did at the beginning of this course. Basically, at the beginning of this course, we were defining semantics for programs. But now we want to define semantics for formulas. Okay, so what is the semantic of a formula phi? It's basically the set of all traces that satisfy this formula. So the semantics of phi is a subset of sigma omega. It's a set of infinite words over our alphabet. And remember that our alphabet itself was the power set of our propositional, of our atomic propositions. Okay. So basically, again, the meaning of phi is just the set of traces that satisfy phi. And we can now define semantics. Let's try a rule-based semantics, which is kind of similar to how we defined operational semantics. So let's say that I have a trace tau, and it's tau0, tau1, blah, blah. And tau0 is basically in this alphabet, right? So every letter here is a subset of P. And P was the set of my atomic propositions. So I have this trace, which is infinite. And I say that tau satisfies a formula phi if and only if tau is in the meaning of phi, in the semantics of phi. So let's just, instead of defining this, I can just define this relation. I can define basically when a trace, an infinite trace, satisfies a formula. Okay, and to do this, I just need a little bit of notation that we had in the previous sessions as well. So I write this, I basically write tau ij to denote the part of tau that starts from index I and goes to index j. And I also use tau I without anything here to just show the suffix of tau that starts at index I. So I'm ignoring everything until index I minus 1. I'm just trashing them and only looking at index I and everything that comes after that. And that's tau I, or basically the suffix of tau starting at index I. Okay, now I want you to help me fill out these rules. So when can we conclude that some trace tau satisfies the formula true? What should I write as the precondition of this rule? Well, this one is actually the easiest one, right? I don't need any precondition. Everything satisfies true. Okay. Now let's look at this one. So when I say that tau satisfies an atomic propositional formula P, an atomic proposition P. So before I told you that when we just use a proposition without any temporal operators, what we mean is that this proposition should hold at time 0, right? So an infinite trace tau satisfies P if and only if the first index of tau, tau0, includes P, right? So what was the first index of tau? This was the first letter, and each letter was a set of atomic propositions that hold at that point in time. So basically what I'm saying here is that tau satisfies P if and only if P holds at time 0 in tau. Okay? And then the rules for OR are basically the same as what we've seen for programs. So if tau satisfies phi1, it satisfies phi1 or phi2. If tau satisfies phi2, it satisfies phi1 or phi2. And the rule for negation is also just the same. So if tau does not satisfy phi, then tau satisfies negation of phi. That's just the definition of negation. But there's actually something that I have to say about these rules. And it's that these rules are reversible. They're two-sided. So they're if and only if rules. So I can basically swap the two sides, and that's also a valid rule, right? So it's not just that if tau does not satisfy phi, then tau satisfies negation of phi. It's if and only if. Tau satisfies negation of phi if and only if tau does not satisfy phi. And this applies to all of my rules. So I'm not just going to write two copies of each rule, just know that these are if and only if rules. Okay, but here's the interesting part. So what happens with the temporal operators? When can I say that my trace tau satisfies next phi? What should I write as the precondition for this rule? So what does next phi mean? It means that if you ignore the current time and start the time at the next iteration, at the next time step, next second, whatever it is, if you start at the next time point, then phi should hold. So let's write exactly that. So let's just take the suffix of tau that starts from index 1, the suffix that ignores index 0. And let's say that if that suffix satisfies a formula phi, then tau satisfies next phi. Okay. What about until? So when does tau satisfy phi1 until phi2? I'm not going to tell you this one. I'm going to wait for you to figure it out. So what should I write up here? When does tau satisfy phi1 or phi1 until phi2? So the idea was that there should be some point in time such that phi2 holds at that point. And then at every point before that, phi1 should hold. So let's just write exactly that. There should be some index j, some point in time j, such that if I only look at the suffix that starts at time j, then this satisfies phi2. And also at every time before that, at every I that is less than j, if I only look at suffix that starts from the suffix that starts from I, then this should satisfy phi1. And if I have these, I can say that tau satisfies phi1 until phi2. Okay. And this is actually the end of the formal semantics of LTL. I don't need to define formal semantics for eventually and globally or always. Why? And this is because, well, these were syntactic sugar. And because they were syntactic sugar, I can just use the other rules. But anyway, let's define these rules as well. So when does tau satisfy eventually phi? Well, this means that there should be some point in time such that if you take the suffix from that point onwards, it satisfies phi. So this is basically that. There exists some index I such that the suffix of tau starting from I satisfies phi. And for the other one, for globally phi, we just need phi to hold at every suffix, right? So we need phi to hold at every time. So this would be it. So for every time I, if I only look at my system from time I onwards, then that trace also satisfies phi. Okay. So these were the formal rule-based semantics of LTL. But now let's look at something else. So what I really want you to realize here is that what we're doing with logics with LTL is quite the same as what we were doing with automata and what we were doing with games. These are just three different viewpoints on the same types of problems, the problems that work with sets of infinite words. Okay, so let's actually show this, and let's show how we can write our classical objectives from the game part in LTL. So again, let P be my set of atomic proposition. Let's say that my alphabet is the power set of P. And let's look at traces on this alphabet. So for a given proposition P, I define AP as the set of all letters that include P. Again, remember that my letters are sets of propositions. So this makes sense. AP is the set of all letters that include P. Or in other words, AP is the set of all subsets of big P that includes small p. Okay. If this is my definition, then how can I write reachability of AP in LTL? So give me a formula that models this objective, the objective of basically reaching some state where P holds. How can I write this in LTL? Yes, it's just eventually P. Actually, to be completely formal here, because this thing, this was an objective, right? So it's a set of traces or set of infinite words. We have to take the meaning of eventually P because that's also a set of infinite words. So yes, if your trace, if your infinite path satisfies eventually P, then what does that mean? It means that it eventually reaches P. So it's the same as reachability. Okay. How about safety? What is safety in AP? This is, again, safety was the dual of reachability, so you can just take the dual here as well. It's the same as the meaning of always P. So what does always P say? It says that you should always stay in the states where P is satisfied, right, where P holds. So it's the same as saying that you have to be safe inside AP. Okay, but the nice ones are Bookey and co-Bookey. So how do you say Bookey of AP? So Bookey of AP would be the set of traces that visit P infinitely many times, that visit a state where P holds infinitely many times. Yes, that's correct. This is exactly what we saw in those examples, at the end of those examples. It's always eventually P. So if you have always eventually P, of course, you're going to see P infinitely many times, and that's the same thing as Bookey. How about co-Bookey? Yes, it's eventually always P. And this is, again, because of the duality. So Bookey and co-Bookey are duals. You can take a dual here. But also, we talked about co-Bookey in the sense that when we want co-Bookey of a set T, what it means is that we have to just ignore a prefix. And after ignoring a prefix, you always remain in that set, in your target set, right? And your target set here is the set of states that have P in them. So, oh, this is a typo. Okay. So this is the same thing as what this formula says. This formula says eventually. So whenever you see eventually, that means that you can basically ignore a finite prefix. After ignoring a finite prefix, you have P all the time. So this is co-Bookey. Okay, and now let's also see how we can do parity. Parity is the most interesting one. So let's say that the set of our atomic propositions is exactly the set of priorities. So at every point, we know that we are either at priority 0 or 1 or T. And let's say that this is our set of priorities under some priority function Q. How would we get the parity objective? So the parity objective is the set of all traces in which the minimum priority that is seen infinitely many times is even, right? So how can we say this in LTL? How can we say that the minimum priority that is seen infinitely many times is even? So the important point here is that the number of priorities is finite. We have d+1 priorities. So what we actually want to say is that the minimum priority that is seen infinitely many times is either 0 or 2 or 4 or 6, so on, until we reach t. So can you write that in LTL? Any ideas? Actually, this is very much similar to what you should do for translating parity conditions to Buki conditions in automaton. That's one of the homeworks. So maybe I shouldn't show you this, but well, I will show you. So any ideas, really? Okay, so this is it. So you either see 0 infinitely many times, or you don't see 0 infinitely many times, and you don't see 1 infinitely many times, and you see 2 infinitely many times. So this is when your parity is 0, this is when your parity is 2. This is when your parity is 4. You don't see 0 infinitely many times, you don't see 1 infinitely many times, you don't see 2 and 3 infinitely many times, but you do see 4 infinitely many times. Right? And you just write this formula up until D. So a parity condition, a parity objective can also be written like this as the semantics of an LTL formula. So this already shows you the relationship between the logical point of view and the game point of view. We are going to see a lot more of this. Okay. But let's go through something else now. Let's talk about equivalence. So we talked about equivalence in the context of automata. We basically said that 2 different automata are equivalent if they have the same language. Now, here in case of LTL formulas, we don't have any automaton anymore, but we still have the language, right? Because what is the semantics of an LTL formula? The way I defined it, it's just a set of infinite words. And a set of infinite words is a language. So just like automata, we can say that 2 formulas, phi1 and phi2, are equivalent if they have the same language. Or people usually say they are semantically equivalent. Basically, if the semantics of phi1 is the same as the semantics of phi2. Or in other words, for every trace tau satisfies formula phi1 if and only if tau satisfies formula phi2. And we can see a lot of examples of equivalence between LTL formulas. So the boring examples are the ones that are inherited from propositional logic. So not phi is equivalent to phi. We know that, of course. Or for example, not phi1 and phi2 is equivalent to not phi1 or not phi2. And actually, it's quite easy using the semantics to show that any equivalence that holds in basic propositional logic holds here in LTL as well. So these are the boring ones. But the more interesting examples are the ones that actually include the temporal operations as well. So for each one of these, I want you to tell me whether it holds or not. So the first one is this. Does this hold? So not next phi, is it the same as a next not phi? Who says no? How many people say no? Let's do a poll. Any naysayers? Okay, so everyone thinks this holds. It holds actually, yes. So why does this hold? When I say why does this hold, there is a formal answer, which is basically going back to the semantics and actually showing that the semantics of these two formulas are the same, right? And to do that, you have to take a trace and assume that that trace satisfies this formula and show that it satisfies this one using the rules. And then do the opposite. Assume that the trace satisfies this formula and show that it satisfies this one. So we're not going to be that formal right now, but give me some informal intuition why this should hold. So what does this say? It basically says that it is not the case that phi holds in the next state, right? So if phi does not hold in the next state, then the negation of phi should hold in the next state. And you can do this on the other side too. So these two are actually equivalent. Okay. So let's go to next one. Are these two formulas equivalent? The first one says eventually phi1 or phi2. The second one says eventually phi1 or eventually phi2. So we are distributing here. Can we have this kind of distribution? So you said yes. Why? Again, we can just use the definition, right? So eventually phi1 or phi2 means that there is some point in the future where at that point, either phi1 holds or phi2 holds. So we can use the same point for the formula on the right side, right? So if phi1 holds at that point, then we have eventually phi1. If phi2 holds at that point, then we have eventually phi2. And you can also do it the other way around. If the formula on the right holds, then this means that there is either a point in the future where phi1 holds, in which case in that same point, phi1 or phi2 would hold, or there is a point in the future where phi2 holds, in which case in that same point, phi1 or phi2 would hold. So this is also true. What if we do it with and? Okay, why not?
That says phi1 and phi2 at the same time, right?
Right. Okay, so this is the important point. So what the first one says is that phi1 and phi2 should hold at the same time sometime in the future. So there is some time in the future where both phi1 and phi2 hold at the same time. But this second one just says that there is a time in the future that phi1 holds, and there is some time, maybe some other time, that phi2 holds. And because these two times are not the same, these two formulas are not the same either. Okay. What happens if instead of eventually we use globally? So is globally phi1 and phi2 the same as globally phi1 and globally phi2? Yes, right? So what does this say? It says globally phi1 and phi2. This means that at every point in time, both phi1 and phi2 hold. So of course, at every point in time, phi1 holds, and at every point in time, phi2 holds. And you can also do the opposite, right? If at every point phi1 holds, and at every point phi2 holds, then at every point, both of them. Okay, and the last one is globally with OR. So globally phi1 or phi2, is it equivalent to globally phi1 or globally phi2? And this is again, no. Why? Because just consider a trace that alternates. So at odd positions, it satisfies phi1. At even positions, it satisfies phi2. Then it will satisfy this one, but not this one. Again, the problem is whether these satisfactions are achieved at the same time or not. Okay? Nice. And actually, another way to see these last two examples was that they are just duals of the previous two. Okay. So let's see some more equivalences. Tell me if these equivalences hold or not. So phi1 until phi2, is it equivalent to phi2 or phi1 and in the next state phi1 until phi2? This actually holds, and let's just see the intuition behind it. The intuition is that if what does the formula on the left say? It says that there is some point in the future such that phi2 holds at that point, and at every point before that, phi1 holds. Okay? So I can do a case analysis. Either that point in the future is right now, and phi2 holds right now, or if phi2 does not hold right now, then phi1 should hold right now. And then from the next step, I have the same situation as I had, right? So this is the intuition behind this. And actually, you can prove it using the formal semantics, but just let's not do that. Let's agree that this works. Okay. What about this one? So eventually phi, is it equivalent to phi or in the next step eventually phi? Yes, again, this is the same kind of casework. What eventually phi says is that there is some time when phi would hold. So we can do a casework. Either phi holds right now at time 0, which is phi, or we go to the next time step and then phi should eventually hold. So this is also true. And well, again, because these are duals, you can just take duals, but let's do this manually as well. So globally phi is equivalent to phi, and from the next step, globally phi. This is again very obvious. Globally phi means that phi holds at every step of the time. So it holds right now, that's phi. And if I go one step further in time, then it will also hold forever from that point. Right? Okay. So why was I actually interested in these weird equivalences? The reason is that I now want to define denotational semantics for LTL. And I need these for defining the denotational semantics. So if you remember our points about operational and denotational semantics for programs, operational semantics was very similar to these rule-based semantics that we have here. But in case of denotational semantics, the idea was that we want to really define this set. The set that is the meaning of an expression, or in this case, an LTL formula. Okay, so let's just try to do that. What is the meaning or semantics of true? It's the set of all infinite words that satisfy true, which means that it's just the set of all infinite words. Sigma omega. Okay. So what if P is an atomic proposition? What is the semantics of P? What is the meaning of P? Well, we define this as the set of all traces such that P is included in the first letter of the trace, right? And we can write it exactly right like that. It's the set of all tau, and tau is a member of sigma omega. So the set of all infinite words such that P appears in the first letter of this infinite word. Okay. One point that I have to mention here is that I'm only defining this denotational semantics for the main components of my logic, and I'm ignoring the syntactic sugars. So I'm only defining it for formulas of this form. And I don't care about syntactic sugars because, again, this can just be rewritten. Right. Okay. So what if we have OR? So phi1 or phi2. This is just like propositional logic. There's no difference. So a trace satisfies phi1 or phi2 if it satisfies phi1 or it satisfies phi2, right? So you just take the union. And the notation is a bit confusing. This is not until, this is union. Okay. And similarly, when we're talking about negation, so a trace satisfies negation of phi if it does not satisfy phi. So the meaning or semantics of negation of phi is just all those infinite paths or all those infinite traces that are not in the semantics of phi. Okay. Now we get to the temporal part. So how should we define this, the semantics of next phi? So what was the definition that we had before? Like what kind of infinite traces satisfy next phi? Yes, so it's basically the set of all traces tau, such that if you ignore the first letter or the 0th letter of this trace, and you only look at the suffix that starts at time 1, that is in the semantics of phi, right? So I want phi to hold from the next time step. So I just ignore the current time step, which is step 0, and only look at the suffix of tau that starts from index 1. And if that suffix satisfied phi, then the current suffix satisfies this. So this is that. And I can basically write this in the following shorthand. I can just write sigma, and then the set that was the semantics of phi. And what I mean here is concatenation. So you can take anything in sigma and put anything from the semantics of phi after it, and that would be the semantics of next phi. Okay. The really nice case is the case of until. So how do you define the semantics of phi1 until phi2? And this goes back to when we were defining semantics for the while programming language. And if you remember, what we did for while itself was that we came up with some function such that the semantics of while was a fixed point in that function, right? And then we said, okay, so we define it as the fixed point. So let's do something very similar here. And this is why I kept this equivalence up there. Okay. So what happens if I just take semantics of both sides? These two are equivalent, so their semantics should also be equivalent. So semantics of this, which is what I want to define, should be what? Should be semantics of phi2 union with the intersection of semantics of phi1 and next of the same thing, right? So I actually have it written here. So I want to define a function f such that this semantics here, this thing, is a fixed point of F, right? So first of all, what is the type of F? Well, it maps languages to languages. And in our case, languages are basically subsets of sigma omega. So it maps subsets of sigma omega to subsets of sigma omega. And how does it do that? So just look at this and try to define this function in a way that the semantics of phi1 until phi2 becomes the fixed point. So I just let's call this thing x. I can put x here as well, right? So I can define f of x as the semantics of phi2 union, and this is because OR was union, right? Union with the semantics of phi1 intersection, and this is because and is intersection. And this part, what is this part? This is next, do whatever it was in X, right? So, and the semantics of next was just adding a sigma, concatenating with sigma. So this is my function F. My function F takes a set X of infinite words, and it computes another set of infinite words, and the set is this, the semantics of phi2 union with the semantics of phi1 intersection with sigma times sigma concatenated with this X. Okay. Now, based on this, let me erase these things. So if I plug in the semantics of phi1 until phi2 in this, and again, this is a bit, I'm sorry about this, but this is until, this is union. So you have to just look at the types of things to realize what is until and what is union. So basically, this semantics should be the fixed point of this function f, right? Because when I apply f to this semantics, it's basically applying f to this, which gives me this one on the right, and I know that they should be equivalent. So the semantics of phi1 until phi2 is just a fixed point of this function f, which is kind of a weird function. But again, we have the same problems that we had in case of the while programming language. Does this function even have a fixed point? What happens if it has more than one fixed point, and so on? And actually, the solution is the exact same thing as that case. So it has a fixed point. Why? Because we can create a fixed point using our rule-based semantics. And the fixed point might not be unique, but we have to take the least fixed point. Again, why? Because we want it to match with our rule-based semantics. And so this is the denotational semantics for phi1 until phi2. It's the least fixed point of the function f. And this was the function f. Okay. And of course, we can define denotational semantics for eventually and globally in the same way, or we can just say that these are syntactic sugar and we have defined semantics for everything else. So whenever you see this, just rewrite it using the other operators and then apply their semantics. Okay. So that's it for this session. You can generally leave at 5:50. You never have to stay after that. But if you have questions, please stay and ask. Okay, so I'm stopping the recording so that, oh, okay. This is, I thought I hadn't started.